So this problem deals with an infinite series, which converges to some value s, and some continuous function, which matches each term of the series for its input values, and our function is positive and decreasing. This means we'll be using the integral test. All right, what are we supposed to prove? We're supposed to prove that if r sub n is s minus s sub n, then r sub n is bounded by the definite integral of f of x from n to infinity. So what does this all mean? Let's get a grip on this. S is the infinite sum, so add up all of the terms. But s sub n is the nth partial sum, which stops here. This means that for our infinite sum, all of the terms after the nth term is what's left over. If we're talking about the nth partial sum, then this stuff is the remainder. So the infinite series, the infinite sum, is equal to the nth partial sum plus the nth remainder. So if n was 17, the 17th partial sum would be the sum of the first 17 terms, and then the nth or 17th remainder would be term 18 plus term 19 forever. All right, so now if we solve for r sub n, we can see that it's equal to the infinite sum minus the nth partial sum. This is how they said it in the problem. Now, if you're trying to figure out what the infinite sum is equal to, we can always estimate it with the nth partial sum, and we'll get closer and closer to the actual infinite sum that the series converges to as n gets bigger and bigger and bigger. So the remainder gives us an idea of how close our nth partial sum is to estimating the infinite sum. And that's why this theorem is important. It gives us an idea to talk about how close we are with the nth partial sum to the infinite sum. If we know that the remainder is bounded by, let's say, 0.1, then we know that the partial sum is within 0.1 of the actual infinite sum. Okay, so if we stop at the nth partial sum, how can we guarantee that the remainder, which is like an error, because that's how far away we are with our nth partial sum from the actual infinite sum, how can we prove that this error can be no bigger than the definite integral from capital N to infinity? That's what we're going to prove right now. Here's our function y equals f of x, and our infinite series begins with term a sub 1 plus a sub 2 plus a sub 3. However, with these Rm rectangles, the area of this rectangle is width times height. Width is 1, height is a2. So the sum of all these Rm rectangles really starts with a sub 2 and goes forever to the right. These n terms are still the nth partial sum, and everything else is the remainder. It's the rest of the terms. So if we look at how this relates to the picture, a sub n plus 1 is this height, and so this represents the area of this rectangle whose width is 1 and whose height is a sub n plus 1. So that's the area of the yellow rectangle. This is the area of the second yellow rectangle. And if we add the infinite number of yellow rectangles, that's our nth remainder. And we can see quite clearly that the sum of those rectangles is bigger than 0 and less than the area under the curve starting right here. And that's all we needed to prove. Let's write it down. That's it. Quod erat demonstratum. And then if you look at number 55, this shows the usefulness of the conclusion that we just deduced here in number 53.